Welcome. Let's take a look at the definition for absolute maxima and minima. Let f of x be a function defined over an interval I, and let a be a value, an x value, within that interval. We say that f has an absolute maximum on that interval at a if f of x is less than or equal to f at a for all x in that interval. That is, f of a is the largest output value of all x values in the interval I. We also say f has an absolute minimum on an interval at a if f of a is less than or equal to f of x for all x in that interval. That is, the output value when x is equal to a is smaller than the output values for all other x values in that interval. If f has an absolute maximum on I at a or an absolute minimum on I at a, we say that f has an absolute extremum on the interval at a. So let's go ahead and take a look at a theorem that talks about these two types of maximum and minimums. We have the extreme value theorem, and it says if f is a continuous function over a closed bounded interval ab, there is a point c in that interval at which f has some absolute maximum over that interval. And there's a point d in the interval at which f has an absolute minimum over that same interval. So let's take a look at this function we have here on the right. A nice parabolic function. It is continuous. There are no jumps, gaps, holes. And so let's go ahead and look at f of x on the interval from -2 to 2. Now, as we're looking for the absolute maximum, we're looking for the largest output value and where that occurs. Well, my largest output value appears to be here at 1, and that happens to occur where x is equal to 0. So the c that is mentioned in this theorem occurs when x is equal to 0. So we could say that f of x has an absolute maximum. I'm reading absolute and I'm abbreviating maximum of, now the absolute maximum is that y value. So our absolute maximum here is 1, and that absolute maximum occurs at x equals 0. So now we need to think about minimum, absolute minimum. And we are, because this function is continuous on the interval, we are guaranteed there is a point d at which we have an absolute minimum. So now we're looking for the smallest output value, or the lowest or y value. And we can see that that actually happens at two locations. It happens at -2, 3 and at 2, 3. So while the theorem guarantees there is one point or a point, there can be multiple points, as we see in this case. So one of those values, we'll call that d1. That occurs at -2. And that other value, we'll call that d2, occurs at +2. So we could say that f of x has an absolute minimum of, now the minimum is that output value, and I'm sorry, those are not +3s, those are -3s. So has an absolute minimum of -3 at and now there are two locations, x equals -2 and x equals 2. Now let's take a look at a second function. Notice that we have a function here that 2 is nice and continuous. And so if f is continuous over a closed bounded interval, so let's go ahead and look at f of x on the interval from -2 to 2, including the endpoints. We do satisfy the hypothesis of this theorem. We are guaranteed a point C where there is an absolute maximum and a point D where there is an absolute minimum. Now, looking at our graph here, we're looking for the absolute maximum, which is the largest output value or the largest y value. And we can see from our graph that that's going to be a y value of 3. And that happens at two locations. So we have two C values that produce this absolute maximum. So we could say that C1, or the first of those values, is -2. And we could say that C2, or the second of those values, is +2. Now, so what can we say? Well, we can say that f of x has an absolute max. Now, the absolute max is that y value, that largest output value, and that is 3 of 3 at, and then now we give the location where that output value occurs, and that occurs at x equals -2 and +2. Now, we are also guaranteed an absolute minimum. So this will be our lowest or our smallest output value or our lowest y value. And we can see that that happens here as the curve crosses through the y-axis. And that lowest value is -1. And that occurs at x equals 0. So we could say that that d guaranteed by the theorem is equal to 0, because that corresponds to our lowest output value or our smallest output value. So we can say f of x has an absolute minimum of, now absolute minimum is that output value, and that output value is -1 at, and now we give the location, and that occurred at x equal 0. Now let's take a look at one more example. Now notice that in the extreme value theorem, the hypothesis is that we have a continuous function over closed bounded interval. Now, from our graph, we can see that we have a function that is defined from -1 up through 5. So we could have a closed bounded interval. We could say we're interested in f of x on the interval from -1 to 5. However, we have a small problem. The requirement here is that this function be continuous. Well, this function is not continuous. Notice we have a jump discontinuity occurring at 3. So what this means is that for this particular function, we are not guaranteed the existence of an absolute maximum or an absolute minimum. Now, we may have one or the other or both, but we're not guaranteed that those exist. So let's go ahead and first think about identifying whether there's an absolute maximum. So in terms of an absolute maximum, again, we're looking for the largest output value or the largest y value. And as I look at the graph of this function, I notice that that is occurring here at 6. So the point at which we have our absolute maximum, we do have one, occurs right there. And it occurs where x equals 0. So we could say that f of x has an absolute maximum of, we said 6, that's the output value of 6 at x equals 0. Now let's take a look and see if we can identify an absolute minimum, or a smallest output value, or a lowest y value. And as we look at our graph here, we can see that except for this interval from about 2.5 to 3, the rest of the output values are positive. So if we're going to have a minimum, it's going to occur, an absolute minimum, it's going to occur below the x-axis. And what we can see is that this function to the left of 3 continues to drop and fall, and it looks like it's getting close to -3. But we have to notice that there is an open circle there, which means that when x is equal to 3, the output value is not -3. What this is telling us is that as we get closer to 3 from the left, our output values are getting closer and closer to -3, but never actually reaching -3. So if these are getting closer and closer to -3, let's say 2.9 and 2.99 and 2.999 and -2.9999 and so forth, these are getting closer and closer to -3, there's not going to be a smallest value. You could give me a number close to -3, but not equal to -3, and I could give you another number smaller than that, that is even closer to -3. So we can never really reach that -3. There will always be another number between any given output value slightly larger than -3 and -3. So for that reason, because this never actually attains a y value of -3, and that if it did, that would be our absolute minimum, but it doesn't, so it can't be our absolute minimum. We have to say that f of x does not have an absolute minimum. I hope you find this helpful.